Okay, so we're going to invite up Arasu Arun and Michael Zhu to talk about Jolt, SNARKs for virtual machines via lookups. Welcome. Right. An applause.
Okay, yeah, thanks. Yeah, I'm Arasu, and this is Michael. And do I have the clicker?
Is it?
Oh, sorry, it's here. Yeah, we're here to talk about Jolt. Jolt is a ZKVM, and I'll talk about the quick technical overview and the moving pieces that are involved in Jolt, and Michael will go deeper into the implementation and performance details. Right. Okay, so just to establish some notations, so Jolt is a ZKVM, and what we want to do is take some machine, like a CPU or a virtual machine, and we want to represent it as some sort of intermediate representation. You can think of this as like R1CS, Plonk, CCS, AIR, whatever you like. And this, I'll be calling this a CPU circuit throughout. And what this does is it acts like a universal circuit that takes programs for that machine, and along with some other inputs and outputs and possibly advice. And this is fed to the backend, which proves that this program on these inputs gave the claimed output, along with some possible advice inputs and so on. And the backend is what you would think of as a SNARK proving algorithm like Groth16 or a polynomial IOP like Spartan, Plonk, so on. All right. I feel like I'm kind of preaching to the choir here, but ZKVMs are really cool. A few advantages, like we have one circuit that can run all programs. You don't need to compile a specific a circuit for every new program that comes by. You can also reuse infrastructure, especially if you're working with real-world CPUs like RISC-V and the EVM. You can reuse the languages, the tooling, the compilers that already exist. And notably, you can also focus all the auditing efforts onto one circuit, or the engineering optimizations effort onto one circuit, and so on. But of course, there's a catch, and that's because there are a lot of overheads that are involved in designing these CPU circuits. So I'll talk about a couple. The main one is that because we want to handle arbitrary programs, each step must handle every possible instruction that can come up. And there's a lot of instructions, like RISC-V has 50, the EVM has almost 150. They're all like very varied instructions. They perform different things like memory to bitwise arithmetic and so on. And you can optimize this. It doesn't have to be a simple switch case of all the instructions, but the prover will inevitably have to pay for operations that they are not executing at that step. And this overhead is seen in like the field operation costs or the commitment costs and so on. Another thing I'd like to note is that the bitwise operations, like these primitive instructions are made for bitwise operations. And that's not very amenable to the intermediate representations that we have because our circuits are all like field elements. So we'd have to do bit decompositions to actually realize these operations, which could be costly too. So the goal of Jolt is to get rid of these overheads, basically. And we want to design a circuit where we only pay for the instruction that's happening at that step. And we do this by designing a pretty minimal circuit that just performs lookups to a table that's outside the circuit. This leads to a very small circuit, and it's for RISC-V 32 bits, it's just 60 constraints, and the circuit takes about 80 field elements per step. How does this really work, though? What's like the underlying technique? Well, it turns out that primitive assembly instructions have interesting mathematical structure, namely that they have like very efficient to evaluate polynomial representations. We'll get more into this later if this is a bit abstract. And we leverage this to perform structured lookups using an algorithm called Lasso that was designed in companion with Jolt. And hopefully in this talk, we'll convince you that this leads to a very modular and easy to extend framework for designing ZKVMs. All right. So a brief introduction to how circuits are actually built. Well, we have a machine state, and that includes like the program counter, program code, registers, RAM. This is like the RISC specification, but like pretty much the same for most CPUs. And we have a transition function. You may have heard of like the fetch, decode, execute loop. And this is applied to the machine state repeatedly, and that's how your program is run. And we want to take this function and turn it into an arithmetic circuit. And if you have an n-step program, the circuit is just repeated for each step of the program. Right, so I'll quickly talk about memory checking because we use existing techniques for that. But all of these many of these instructions would operate on these bodies of memory, like the registers, program code, and RAM. And we need to be able to handle reads and writes in a secure way because the provers aren't trusted. So we use this technique called offline memory checking that was actually described like 30 years ago in a paper by Blum et al. And that was adapted to SNARKs in a paper called SPICE in 2018. The gist of it is that if you have a sequence of memory operations, you can reduce consistency checking for that sequence into a multi-set equality check. And we perform this using like a GKR-style grand product argument. So you can just think of this as a black box. You have a list of memory operations, some reads and writes. You send it to this offline memory checking algorithm, and it gives you a proof. And this proof is linear time in the memory operations and the size of the memory. Right. So let's get to the instructions. So we don't want to do all the instructions in a circuit. So let's try to offload it outside. So imagine that you had a table that was pre-processed with every possible opcode and the inputs that the operation can have and the outputs, right? So this is for RISC-V. We have a big table for all of the instructions. And it's kind of like a cheat sheet for the CPU or like a Boolean, like a truth table for the CPU, you can kind of imagine. So if we had this, instead of doing a fetch, decode, execute, we just do like a fetch, decode, lookup, right? So we send in the opcode and the operands, and we get back the output. And there are lookup arguments that can do this, but not for tables this big. Like even for 32-bit entries, these tables are like 2 power 64 in size. For 64-bit entries, like you can't even materialize this table. It's just way too big, right? So it looks like we can't really use lookup algorithms over here. But the interesting thing is, and this is the main observation I alluded to earlier, is that these tables have a very nice structure. And that structure allows us to never have to materialize them. We have a very nice representation of it. And that representation is basically that the tables, every instruction's input to output mapping, can actually be represented as a polynomial over the bits of the program's inputs. I don't want to get too deep into the weeds here, but like a few examples of these polynomials are like the XOR polynomial is over there. The less than operation can be written like that. The shift. Basically, what I want to convey is that since these operations mostly perform like bitwise manipulations, you can imagine that if I give you the bits as variables, you can design a polynomial that basically executes the instruction. Right. OK, so why is this exciting? Well, that's because polynomials are really like the language of SNARK backends. So given the fact that all these primitive instructions actually have really nice polynomial representations, can we use this to design better ZKVMs for machine proofs and so on, right? So if there's one takeaway from the idea of Jolt, that's basically this, right? Turns out we can also get a slightly better or more favorable representation for us. Instead of just a polynomial over the bits of the inputs, you can chunk the inputs, feed each chunk to its own smaller polynomial, which we call like subtables, and then combine them together to get the main table. Right, so for a 64-bit operand, we have like 8 chunks and so on. And turns out that you only need 23 unique subtables to represent all RISC-V instructions. So basically, these small 23 subtables span every RISC-V instruction, at least in the base set that we need. Right? OK, so
yeah, for the base integer instruction set. Yes.
Yeah, but we can also do the multiplication extension and so on. It just requires a few more subtables, but yeah. Right, so I'll just give a quick overview of how the lasso algorithm works. The core tool is like a sum check and a memory checking, and it's built on, if you heard of the Spark compiler in Spartan, it's built on that. So we give a trace of instruction lookups, and what this involves are the operand chunks, the subtable outputs, the memory checking timestamps, and all the flags that indicate which of the subtables are used for this instruction. Kind of feed it to the lasso algorithm, and it gives us a proof that all the lookups are actually consistent. Right? And just a quick note on the performance. It's linear in the number of lookups that you perform. And adjusting like the chunk size, you can actually get, even if the table is very large, you can make the prover actually very efficient. OK, so we've offloaded a lot of work to the memory checking and the instructions. So what does the CPU circuit actually do now? It's really simple. It just maintains like the correct program counter every step. And it takes these traces as advice, and it performs some simple consistency checks. So for example, it makes sure that the values that you read from the registers are really what you're sending as operands in the lookup. Really simple. For, again, 32-bit RISC-V, we only need about 60 constraints to actually do all of these checks. Okay, so putting all of this together, we have like a very modular Jolt prover. We again feed the trace of memory operations. The prover like executes a program, feeds this trace of lookups and the memory operations to like this Jolt prover, which has 3 modules for the lookup argument, the consistency checks, and the offline memory checks. And totally, it's about 80 elements per CPU step. I think if you go to 64-bit RISC-V, you go to like 100-ish elements and so on. But basically, they're like very small, very like small number of elements, and you get 3 proofs at the end. Right. So I just want to get a quick overview of like the commitment and prover costs. I do want to highlight though that you can plug and play with your own algorithms over here. We used Lasso and Spartan and Spice for memory checking, but you don't have to do the same thing. You can, this is like a pretty flexible module. It's just that for us, because we use these particular protocols, our backend is just all sum checks and some evaluations on multilinear polynomials. It's like very uniform sort of backend. And the commitment costs, most of the elements involved, even though there are 100 elements per step, they're really very small. So if you use like the Pippinger's algorithm, we use the Hyrax polynomial commitment scheme, by the way. It's equivalent to coming to about like 11 arbitrary 256-bit long field elements because most of them are actually pretty small. And the prover is linear time, so we don't have to perform any n-log-n operations like sorting, for example. And again, mostly sum checks and so on.
All right, yeah, so I'm going to talk a bit about our implementation of Jolt. So we released an initial implementation of Jolt in Rust last month. It's fully open source, MIT licensed. You can find the GitHub repository there, a16z/Jolt. For the instruction set, we're currently targeting the 32-bit base integer instruction set, aka RV32I. But as we said, this framework is highly extensible, so we have some PRs in the works to add the M extension, and we also think it would be fairly easy to support 64-bit word sizes as well. So the Jolt paper itself is agnostic to the polynomial commitment scheme, but the implementation currently uses Hyrax as the default elliptic curve, although you can swap in any ArcWorks supported curve there. And we also are currently working on implementing some additional polynomial commitment schemes, namely zeromorph and Binius, which is over binary extension fields. For the R1CS component, we currently use a fork of Spartan 2, which we optimize to leverage the high uniformity of the Jolt circuit, which, as we said, like we basically use the same handful of constraints for every step of the CPU. Right, so we've talked a bit about how easy it is to implement and test instructions in Jolt, but to make that a bit more concrete, I'm going to walk through the flow for one particular instruction, in this case XOR, and for readability, we're just going to look at XOR with 8-bit operands, but in RISC-V, this would actually be 32 or 64-bit. Right, so as Arasu said, the key insight of Jolt is that these CPU instructions are highly structured in that they can be decomposed into a small handful of simple subtables, and then we can perform lookups into those subtables and somehow reconstruct the instruction output from the lookup outputs. So as a first step, we want to figure out what are the lookup indices that we're going to use to query those subtables. And we're going to compute those from the instruction operands. So in the case of XOR, we implement this, this toIndices method as just concatenating different chunks of each operand. So you have you have 4 lookup queries constructed as the concatenation of the left and the left and right chunks of each operand. From there, we want to know which of the subtables to query. So that's what this subtables method is for. So as mentioned, Jolt for RV32I uses 23 unique subtables. So this subtables method sort of tells us what the bipartite graph between the lookup indices on the left and the 23 subtables on the right looks like. So the code here just says we're only querying the XOR subtable, and we're going to query it using all 4 of the lookup query indices. But in general, there's a many-to-many mapping from instructions to subtables. And yeah, so the more complex instructions will use multiple subtables, and some subtables are shared between multiple instructions. Right, so for the lookup output, each of these 23 subtables has its own trait to implement, namely the lasso subtable trait. That basically defines what the contents of the subtables are. So given a lookup query, it knows what the output is. So for the XOR subtable, as you might imagine, it interprets those 4-bit lookup queries as 2 2-bit operands and just performs XOR over those 2 operands. So 1 1 XOR 0 1 is 1 0. And it's going to do that for all 4 lookup queries. And then finally, we need to somehow reconstruct the instruction output from those lookup outputs. So that's what the combine lookups function does. It's, in the case of XOR, it just concatenates all of the lookup outputs together. And you can verify for yourself that that is, in fact, the output of the 8-bit XOR. Right, so now we have this somewhat convoluted route to go from the XOR instruction to the instruction output. But obviously, there's a much easier way to do this, and that's just compute the XOR directly in Rust, right? And that's what the lookup entry method does. And as it turns out, the Jolt prover uses all of the methods displayed on the screen here right now at some point in the proving process. And so these 2 paths need to be consistent with one another. And so a reference test basically falls out of that. So what we can do is compute the instruction lookup, instruction output from this subtables route and compare it to the instruction output as computed from the lookup entry function and just make sure they're equal to one another. And then we can just randomly generate some instruction operands, and basically that gives us a fuzz test of each instruction implementation, which is quite nice. In terms of performance, so the Jolt prover today currently proves 100,000 RV32i instructions per second, so 100 kilohertz on an M3 Max MacBook Pro. And from that, we can kind of compute an estimate of the proving overhead. So that can be written as the CPU clock speed divided by the proving speed. So the M3 has 12 quote-unquote performance cores and 4 efficiency cores with those reported clock speeds divided by 100 kilohertz gives roughly a 600,000x overhead versus native CPU execution. This is another way to look at the prover performance. So we can break it down by what the prover is spending time on. So we can see here roughly half of the prover time is on sum checks and GKR, which uses sum check under the hood. About a quarter is spent on hierarchs commitments. And then the rest is some combination of witness generation, computing polynomial evaluations / hierarchs opening proofs, and just like shuffling memory around, basically. Another way to break it down is, so we've organized the Jolt codebase into 4 modules, proving the consistency of instruction lookups, read-write memory, bytecode, and R1CS constraints, respectively. So this is going to vary based on what program you're proving. And it's a bit hard to disentangle the different modules because all the different polynomials are committed in parallel. But this gives a rough sense of what the breakdown looks like. So we see that R1CS takes the most time, followed by instruction lookups, and then read-write memory, and bytecode is a sliver of that. As far as what's next for Jolt, we see the roadmap as being roughly bifurcated into 2 subtrees. So Jolt today, as we said, uses hierarchs, which is an elliptic curve-based commitment scheme. So one of those subtrees continues down the elliptic curves path. So we have some PR in the works by one of our open source contributors, Pat Stiles, to integrate a non-hiding version of zeromorph as a polynomial commitment scheme. So Hyrax has square root proof sizes and verifier cost, but zeromorph will bring that down to logarithmic. And then also down the elliptic curve subtree, we are interested in exploring folding as a solution for continuations and eventually as a path towards an on-chain verifier. And the other subtree that we're interested in is binary extension fields. So in particular, we're very interested in the commitment scheme from the Binius paper from the irreducible team. So we have some groundwork in progress for that. And once that's integrated, we think we can do self-recursion. In other words, proving the Jolt verifier using Jolt itself. And again, that's another path towards an on-chain verifier. Yeah, so as a heuristic way to think about these two different subtrees, we think Jolt over binary extension fields is going to be a very good general purpose ZKVM. But if you want to prove any statements about elliptic curve cryptography, for example, like ECDSA signatures, then you're going to want to use Jolt over elliptic curves for efficiency. And yeah, there's lots more on the roadmap as well that I'm not going to talk about here, but we're always looking for open source contributors. So if you'd be interested in working on some of these problems, do reach out. Yeah, that's it. We can take questions.
We have two questions. Maybe the first question, if it's long to answer, we can take it offline. One thing that is for me too hard to understand with respect to this lookup arguments for the different instructions is to understand some kind of overhead in trying to map all instructions into the same kind of lookup pipeline, right? You showed AND, XOR, but addition and multiplication perhaps are more complicated than XOR, and you somehow, the whole path has to be unified across all the lookups, right? So I want to understand what is the overhead in like trying to map all of the instructions, and I'll also say the reason I'm asking this is because now you add more instructions, maybe 64-bit is not too much different than 32 bits, but if you want to include floating point, now again, you will have to map this lookup into all the floating point instructions. Again, you have to hand do this, like this is going to be, I'm assuming, quite a bit of work, but I just wanted to know your thoughts.
Yeah, I think about the pipeline at least, yeah, it's really about like dividing, decomposing one big MLE into smaller ones. And what I think I kind of skipped over it, but like when we send things to the lookup argument, we have to give flags indicating which of the subtables are used to combine into this instruction and what the simple like collation function for those are. I think if you put those together, you can get the lasso lookup argument really works on the smaller subtables. And you need another sum check layer on top of that to make sure that they're correct. So that's like the really quick answer to the thing. And also, like we also mapped out like multiplication and floating point extensions, and they're really built on like the same philosophy. Like you can take all the floating like fad, fmul, and so on, and build like a polynomial for each of those as well. Yeah, would be happy to talk about it then later too.
Yeah, I guess I would just add that for, I guess, some of the instructions in the multiplication extension, we map a single instruction to a small constant, like quote-unquote virtual instructions. I think like 7 virtual instructions for some of the multiplication instructions. But otherwise, yeah, the pipeline is similar to what we have now.
I have one more question if there isn't anyone else. Can you go to the pie chart with the GKR thing?
Oh, yeah.
I just want to know, so the sum check part takes, the sum check part takes more than half the time. That's not even public key operations. The commitment is the public key operations. The sum check part is really just 256-bit modular arithmetic operations. And
correct.
Can you give an insight why that's half? And like usually, I would think public key operations are going to be like way more than the rest of the.
Yeah, I guess one thing to note is this is kind of always in flux as we optimize one part or another. But yeah, I think this can mostly be attributed to the fact that we commit to relatively little data, right? So only a handful of field elements per step.
Yeah, we intentionally chose like a commitment scheme that's based on multiscalar multiplication. So if you're committing to a 10-bit value, it's actually a lot cheaper than committing to a 100-bit value. And almost all our values are below 32 bits, so it's like very efficient. And yeah, the sum check is really high because if we have like 1 million steps, that's even though we only have 60 constraints, the constraint system totally is like 60 million, and that really adds up. Yeah. 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 Yeah, exactly. That's why we're really interested in like Binias and so on. Yeah.
Right.
Yeah, I guess one question is, do you have any intuition on how performance will scale?
Oh, sorry.
How performance will scale as the number of instructions increase? Maybe say 1,000 or like.
Do you mean number of instructions in the instruction set or like in the execution trace?
In the instruction set.
Yeah, but we think it'll be pretty favorable because it's all a matter of like cutting it down into MLEs and subtables. So I think that it should, like we were adding multiplication floating points, and we should be able to handle those with just like a few more subtables, maybe a handful of subtables per extension. Yeah, anything to add?
Yeah, so like, for example, if you were to add an instruction that just reuses existing subtables that we currently use, then it's like really only an additional like 1-bit value that we have to commit per CPU step, basically like as part of like the indicator vector of which instruction is being executed.
Thank you.
Yeah, so those are very impressive numbers. So I'm trying to disentangle the contributions from Jolt and from Lasso. Right? So Jolt is described as a virtual table. Right? So is it the same as multiple lookups in each subtables, like compared to other schemes? Or is there some sort of efficiency improvement in like combining them?
Yeah, so Jolt and Lasso were kind of written together. We just split it into 2 papers. But yeah, Lasso did come first as a general like lookup argument for multilinear, where the table can be represented as a multilinear polynomial. And as we also talked about doing it with Jolt, we realized that if you decompose the polynomials, it's like a lot more efficient. So yeah, it's really hard to like disentangle like what is attributed to what, but like definitely the lookup argument as standalone can be used without Jolt altogether. Like if you have a table that's very large but it can be decomposed, you can just use Lasso as is. Yeah.
All right. Do you mind taking it on the break? Okay, awesome. Thank you. So another round of applause for other speakers. Thank you. And I apologize for the previous